All right, what's up, everybody? So today we're going to be talking about Euler's method. So we have discussed the Newtonian approach to how to get equations of motions from there. We've discussed, which, by the way, which is based on acceleration. We've discussed the Lagrangian approach and how it's based on energy, right? Today, the Euler method is actually based on momentum. And it's actually great for rigid bodies, especially anything that involves angular rotation, angular whatever, right? Euler is a very powerful tool with that. The more you have like more degrees of freedom in your system, the more you will find out that, you need to use multiple methods to actually account for all of these things. Okay, so let's talk about Euler. So Euler basically, it all started with momentum equal to mass times velocity. So I think we all know this equation here, right? And I can argue that, okay, so if I were to take this equation and derive it with respect to time, right, I get ma, which is equal to your force, right? Okay, well, from there, right, Euler came up with a concept called angular momentum, right? Which is basically h is equal to radius cross the momentum, right? And if you were to take that expression here and derive it, that expression will give you dH over dt, and that will be your sigma torque. Okay, so again, this is a very powerful method. By the way, if you were to follow what I did here, I took the derivative of the momentum, right, which gave me the force, and then I'm multiplying the force by by some distance, which gives you, a moment. So that's Euler's famous and very powerful equation. Another way to write this, right? So another way we can actually write H as is going to be equal to the matrix of inertias, right, times the angular speed, the angular rotation speed. Okay, so omega as a vector. So from here, again, we can come up with a different interpretation of this equation, which we can say sigma t, right, is equal to d over dt of I, right, matrix, cross omegas. So, by crossing omegas, I mean omega x, omega y, omega z. So yeah, so that's how to solve this. The equation is very simple. Don't judge me, but once we go into this is when I like MATLAB, because you're gonna usually end up dividing, whatever vector you're talking about to an I hat, j hat, and k hat, and this is when things get a little messy and you need to keep track of the cross multiplication of I hat versus j hat, like how does it come out and all this good stuff. All right, well, let's try an example. Well, again, I told you it's great for rigid bodies, right? So let's try a rigid body example, even though it's kind of cheating, but I'll explain why. So let's say I have this block, right? And I'm going through this point here, which I'm going to call my point A, and I'm fixing that block. So that block is basically free to rotate in this direction, but nothing else. Okay, so yeah, that's it. So when I come here, right, the first thing I want to do is equations of motions. I'm going to say, okay, well, my block is exhibiting what acting on it, right? So I have to assume, first of all, so let's see, let's first discuss degrees of freedom. How many degrees of freedom do I have? Well, it can't rotate this way, sorry, it can't move this way. It can't translate up, and it can't translate into the page. So I have one rigid body. I have no planar bodies, and then the constraints. Sorry, this is close. And then the constraints, I have 3 constraints, right, in a translational direction, and then in a rotational direction, I have 2 restraints because I can't rotate. I can rotate this way, or so I can't. Here's my pendulum. I can rotate this way, and I can rotate this way. I can only rotate this way. So basically -3, -2. So like an overall 5 constraints. So that's a 1 degree of freedom system. That's why I said it's like cheating, because it is a rigid body, but it's a 1 degree freedom system. Okay, well, if I want to try to see if I can explain that better, right? Let's do a free body diagram. So I have some block, right, about this point here. Its center of mass is something here, right? Remember that the gravity force always acts at the center of mass, right? So this is my mg, and I have, let's say, distance from here to here, r. Okay, and this is my point here, my point A. Okay, well, let's see. Well, I only have one force acting on this, right? And that force only, so I can't assume that it's not moving, right? Because if I assume that it is at its location, then where is the problem? Why am I even doing this? There's no motion. It's a static problem, right? It has to move. So when you move it, now we have a problem because we have a force actively acting on it, which is gravity. Okay, so let's do our equations of motion. So, like you remember, I said delta t is equal to, right? So obviously this will be exhibiting some kind of angular speed, right? Omega. And let's call this stuff about the z-axis. So let's call this, or actually let's call it x-axis. Okay. So that being said, so my omega x is equal to dh over dt, which is equal to, as we talked before, right, my inertia matrix, or my inertia, and my omega in whatever direction. So this is simple because I know I only have 1 degree, so I don't have to worry about the rest. So my inertia in this case is whatever the inertia of the block is, right, which is Ixx, and then my omega for that block, which is omega x, right? And then derive with respect to time, so I'm going to have omega x dot, okay? And that's going to equal to my force acting on it, right? So I'm going to assume that up is my situation. Now let's take a closer look about what's happening here. So this is so I have my point here. I have a relation to the center of mass here, and then gravity is acting here. Okay, so I know this is some theta, right, over here, and this is some r. So okay, so let's translate this. So how do we translate it? Where this force will break into 2 components, one in this direction and one in this direction, right? And this became my theta. So this force is mg. Now I have mg sine theta, right, is the force that's acting this way. And now I just have to multiply it by the radius, away from the point that I'm pivoting about to get the torque. So it's going to be times r. So this here is going to be my torque acting on this. Now it is acting in the opposite direction of my motion, right? Because I assumed my direction here this way, right? So mg is going to be acting in the opposite direction. So I'm going to say, sorry, this is probably a bad assumption, but I'll stick to it anyway. And it's going to be minus mg r sine theta. So my equation here became Ixx, right? And then we know that omega is theta dot, right? So omega dot is theta double dot in the x direction. It's equal plus mgr sine theta equal to 0. So here's my equation of motion. Now, there's something we're going to talk about actually, I think in 2 videos here, which is the sine theta approach. Because this now we have a nonlinear differential equation. So one of the things we do is that we can say, okay, we're solving the problem for small thetas. And small angle estimation says that sine of theta is approximately equal to theta. So that means for small angles, right, it's going to be equal to mgr theta equal to 0. So here is our equation of motion. Again, it's very simple, but it gets a lot complicated, as you can imagine, once you have different degrees of freedom and once you actually have a matrix of I and an omega. So one thing I do want to talk about here real quick is that I, right, is derived as, like if I were to say Ixx, I'm going to say Ixx is equal to L square. I'm copying it from a sheet basically because it's a derivative of, if I'm not mistaken, I think it's, let's say, I think it's going to be zz square minus plus yy square over 2 times dm. I think that's what it usually is, because usually what you're trying to do is that you're trying to find the gyration radius and you multiply it by the mass. I don't remember though, however, how it is. Usually you would have some, you'd have a book of references to calculate that, and you use your parallel axis theorem to transfer everything to the point you're referencing to. But yeah, that's the case. I don't have the sheet around me where I have the notes for this, but yeah, it's as simple as this. Euler method is a great method. So if I were to recap real quick, I would say, again, degrees of freedom, right? Understanding free body diagrams, right? With this one, I'm going to say it's very important to understand your coordinates. And this is my screwed up coordinates. So I'm going to say coordinates and points, point references. And then finally, after you do all of that, you can start using, depending on how many degrees of freedom, you might also need to use Newtonian, but you're going to start using dH over dt, which is equal to di, matrix I times the omega vector. Okay. Well, there you have it. And again, this is about a point, so I'm going to say point A, right? So this is all going to be about point A. So yeah, there you have it. If you have any questions, let me know. But again, it's a very simple equations, and most of the solutions, especially when you go more over 1 degree of freedom, 2 maybe it's going to require some math, but it's doable. But after that, you're going to want to go into some MATLAB or some computer analysis based. Why? We're going to talk about that in, I think, 3 videos. But it is basically degrees of freedom is directly correlated to the numbers of frequencies and modes you have, numbers of frequencies, and equals to as well the number of modes you have in in these systems. By these systems, I mean the linear systems, so non-continuous as well. Okay, sounds good. See you next video.